Hello! After watching this video completely, you will have a basic understanding of evolutionary solving. I will show you an example with Grasshopper and explain it every step of the way. Let's get into it. You might have learned of evolutionary solvers or genetic algorithms from some computational design chat, or maybe you watched my video of fitness landscapes. They are algorithms that help us find the best performing values across multiple different variables. The method itself is applicable to many problems, and it is good when we have no clue about where we find the optimal solutions. The downside is that we might land at a subpar peak called local maximum, and without understanding the process, we claim that it is the best that we can do. It is also a brute force method in my point of view, and thus computationally heavy. Let's get to examples. I will be using Galapagos for this as it is available with Rhino and easy to use. At the core, we have a script like this. First, we have the genes. These are our variables or parameters. They can be changed by Galapagos component. Then we have some logic. This is where the calculations happen. This is something that you define. It can be a calculation for steel beams, geometry intersections, just about anything. The important part is that it must spit out a fitness value as an output in numerical form. This is the value that we will either try to maximize or minimize. Imagine it can be the utilization ratio that we want to maximize or weight of all the steel in a structure that we want to minimize. You connect the gene pool and the fitness to Galapagos by dragging from the component instead of to it. Let's move to first demo. This is kept real simple. I have a gene pool that has the values from 1 to 1 million. On the left, we have the fitness landscape of a function that has 1 million values. The logic is just that the fitness is equal to the gene pool value. Let's open Galapagos. For this task, I want to minimize the fitness value. Let's not change anything now and run the analysis. Go to solvers and start. This was reasonably fast as it was just a simple task. Now that the solver stopped, we can look at the results. I'll open the options on the left. In the results window, we have some graphs and some values. The values on the bottom right corner are the population of the selected generations in fitness order. We had the population set to 50, so we have 50 solutions here. We can select the generations from this graph if we want to analyze them more deeply. This graph will also tell us how the analysis has evolved. The x-axis is the generations. The y-axis is the fitness. The red line tells us the average fitness of the generations. The yellow region covers the range of the fitness values in the generation. The orange region is the standard deviation. The graph on the bottom left is to visualize the populations as individuals to see what are the relative concentrations and the distances between populations. Now what actually happens here is that we start with a population that has the population size times the initial boost that gets random values as genes. We then see which genes produce the best fitness. Remember that in this example the goal was to minimize, so the smaller the number, the better. The genes will then breed with other genes and produce offspring from averages. This way, in our example, the whole population moves towards the bottom corner of the slope as each generation gets smaller values and the average moves bit by bit. We have set the maximum stagnant to 50, so this means that if our best fitness value does not change in 50 generations, the solver will stop. This is what happened to us, as we were around generation 52 when the solver stopped. Now we also have the option to adjust inbreeding. Let's move on to our next example to explain this. We now have a function like this. It has two local maximums and one global, the larger peak. Let's use Galapagos to find the x value that will produce the highest y value. I have selected maximum for fitness. If I knew beforehand what kind of value would satisfy, I could set a threshold value and the solver would stop after reaching it. I will now run the analysis. Now that the solver has run, we can look at the results, and they are quite different than in the last one. We have the average fitness value that just keeps getting worse, and clusters of population forming. What do these mean? I will explain this. We had two peaks in the function. Now, some of the population that started from the basins here or here started reaching for the local maximum that I mentioned earlier. Some of the population have climbed to the larger hill and found the global maximum. Now, as we breed them with each other, every generation will create offspring in the average valley, which can be seen here, and also with the red sphere. This is completely normal and expected. Most of the population is still on the peaks, and we can select the best outcome from the list on the right. I can click Reinstate to set the gene pool component in Grasshopper to the values that produce the fitness. Now let's look at the inbreeding. The value has a range of -100 to +100. If the value is set to 100, the genes will only mate with the genes closest to them. At -100, they will avoid the genes closest to them. I can draw two lines on the graph. Now let's say we have a total inbreeding. The genes here will mate within these lines and their offspring cannot ever reach the higher peak. They will get closer to the local maxima. The risk here is with too small population is that the global maximum is never found if we are not lucky with the first generation. Remember, we do not always know what to expect with an analysis like this. If we have no inbreeding and have multiple peaks, the offspring starts to always end up in the valleys and making it harder to move towards an optimal value. If you have questions or requests for videos, please drop a comment below. That is all for now. If you learned something, hit the like button and subscribe to the channel. I will see you in the next one.